All right, we're in section 6.2 where we are going to prove statements about segments and angles. So when we looked in 2.5, we talked about uh, different reasonings or different properties that allowed us to solve specific equations. What this is those are kind of the building blocks that allows us to do what is called a proof. And a proof is a logical argument that shows that a statement is true. Okay. The most common proof that we're going to take a look at quite a bit, not only in this chapter, but in future chapters, is a two-column proof. So the two-column proof has numbered statements and corresponding numbered reasons to show that an argument is in logical order. Okay. Also, we are going to introduce some theorems. So when we're looking at proofs, we are going to be using either postulates or theorems. Postulates are given truths where you don't need to prove them, but theorems are statements that can be proven. You just have to show that they exist in those specific situations or certain examples. So what we're going to do is we have this diagram here, and it has different vertices. And what we have is we have a given statement. We have a given statement that the measurement of angle 2 is equal to the measurement of angle 3. Also, we have that the measurement of angle AXD is equal to the measurement of angle AXC. So looking at this, I'm just going to make some hash marks to help us represent it. So we got angle 2 and angle 3 are equal. So making a hash mark there. And then angles AXD, which is right here. I'll make it a different color. Let's make it a different color. AXD, which is right here, is the same as AXC, which is right here. Okay. So those are given statements. So the first statement that they have here is the measure of AXC is equal to the measure of AXD. That's a given. Okay, it was given to us right there. Second statement here, it says we have the measurement of AXD equals something. And the reasoning that it equals whatever it may be comes from the angle addition postulate. So if I look at AXD, which is right here, angle addition postulate, we have two angles that are showing up here, and we can state that the measurement of angle 1 plus the measurement of angle 2 would satisfy that postulate. You could also use the vertices, but since we shorten it up with numbers, we can use that. The second statement here is also another angle addition postulate, but now it says that it's angle AXC, which is right here. Okay, so AXC is right there. Angle addition postulate, same idea. We can say that the measurement of angle 3 plus the measurement of angle 4 would satisfy that postulate. And again, you could write it with the names with the vertices, but since they have numbers attached to them, we can just use those numbers. Moving forward, we have now it says that the measurement of angle 1 plus the measurement of angle 2 is going to be equal to the measurement of angle 3 plus the measurement of angle 4. So the reasoning for this is a true statement is the substitution property that we talked about yesterday. Because the given was that those two angles were equal to each other, so now we're just setting their angle addition postulate values equal to each other, so then we go from there. Next statement here is we have angle 2 is the measurement of angle 2 is the same as the measurement of angle 3. That gave that to us, so that's a given. Sometimes given statements are not always written on the top, but in this case, this will help us out. So now here we have measurement angle 1 plus question mark is equal to the measurement of angle 3 plus the measurement of angle 3, and they're telling us that it's substitution. So what we're going to do is we're going to kind of look at this statement here and say, okay, this didn't change, this didn't change, and this didn't change, but the one that's going to change is this one right here, and it comes from this statement right here. So what we can say is the measurement of angle 1 plus now the measurement of angle 3 will be equal to each other because of that given statement from statement 5. And then the last one is the proof. The measurement of angle 1 is equal to the measurement of angle 4 because that's what they're asking us to prove right here. And we can say that comes from the subtraction property of equality because we were able to subtract the measurement of angle 3 to both sides, which then they both cancel. So that's how we were able to get that proof. Looking at two theorems when it comes to congruency of segments, very similar to what we talked about yesterday. So it says for any segment AB, when we're looking at the reflexive property, we can say that AB is congruent to AB. All right, it's reflexive. Um, Symmetric one means like if you have AB is congruent to DC, we can just flip them around and say that CD is congruent to AB. And then transitive says that like if AB is congruent to CD and CD is congruent to EF, we can say that AB is congruent to EF. And on the same lines as with segments, we can do with the angles. So if you have it reflexive, we have an angle A, we can say that angle A is congruent to angle A. Symmetric means you just flip them around. Angle B is congruent to angle A. And then transitive means that you're going to look at this one and look at this one and say that angle A is congruent to angle C. So if we looked at the bottom here, if you look at these two statements, we're trying to name the property that best illustrates the statement. For the first one, it is symmetric. And if you look at the second statement, we can say that it is transitive. All right. So now another proof to look at, we have, it says given BC is equal to AB, which they have the hash marks to show that. Um, they want to see that AC is equal to AB plus AB. So there are three statements that we have. The first one was given to us. The second statement here is they're saying that AC is equal to AB plus BC. And the reasoning for that statement is the segment addition postulate. Because if we have two points contained, they will, if you add them together, it comes out to the same line segment. And then the third step is the proof. So if you look here, this did not change, this did not change, but this was a change. All right, it changed from BC to AB. Well, how can we do that? We can do that because we can substitute it because we know that uh, BC and AB are equal to each other, so it's just substitution. Okay. Moving along, we have another proof here. So it says that ray BD, which is right here, bisects angle ABC. So the proof is they want you to say that the measurement of angle ABC is twice the measure of angle 1. So the first statement, like most statements, it's one of the givens. So we have a given statement, BD bisects the angle ABC. Second thing here, we have a blank, but it talks about the definition of an angle bisector. The definition of an angle bisector is whenever you have a ray or a line that bisects an angle, it splits that angle into two equal parts. So since it's going into two equal parts, we can say that this angle 1 and angle 2 are congruent. So angle 1 is congruent to angle 2, and by definition of angle bisector, that is our reasoning. Okay, so if we now go to the next statement, it says definition of congruent angles are equal to each other by measure. So whatever the measure of angle 1 is going to be equal to the measure of angle 2. Moving on down, we have measure of angle 1 plus the measure of angle 2 equals the measure of angle ABC. We can use the reasoning as our angle addition postulate. So if we have this plus this, it equals the whole angle. So it is the angle addition postulate that gives us our reasoning. Next, we have two question marks. We have measurement of angle question mark plus measurement of angle question mark equals angle ABC, and it's from substitution. So again, what we're trying to do here is we're trying to get it twice the angle of twice the measurement of angle 1. So what we're going to say is this is angle 1 and this is also angle 1 because we can change this because of this statement right here, and the substitution property allows us to do so. Then we can then say with the distributive property, we can factor out a 2. So this is 2 times by the measurement of angle 1 will equal the measurement of angle ABC. And that's the proof. Okay, so in this one, we're going to use the symmetric property to show that the segments are congruent. Here, they're telling you that AB is congruent to CD. We can put hash marks there to help us out. That is given to us from right there. The next thing is dealing with the definition of congruent segments. When segments are congruent, they are also equal to each other. So we can say that AB is equal to CD. All right. Now implementing the symmetric property of equalities, I'm just going to flip the two statements around and say that CD is equal to AB, and then kind of doing the reverse idea due to the definition of congruent segments, we can now say that CD is congruent to AB, which is the proof. All right, so this passage here, it says there are two exits between rest areas on a stretch of an interstate. The Rice exit is halfway between rest area A and the Mason exit. The distance between rest area B and Mason exit is the same distance between rest area A and the Rice exit. Prove that Mason exit is halfway between Rice exit and rest area B. So we have this diagram here of how this is going to work out. We got rest area, we got Rice exit, we got Mason exit, we have the rest area B exit. So we have is a given. They're telling you that the midpoint is R, which is the for line segment AM. So I can say that this is these two are equal. Then we can say MB is equal to AR. So I'm just gonna here and here. So actually we can, so I just keep those as two statements to kind of help us out with the proof. So here it says that uh, R is the midpoint of AM and MB is equal to AR, which is given. Next step is they want you to use the definition of a midpoint. Anytime we're talking about the definition of midpoint, it means that wherever that midpoint lies, it is equidistant from one endpoint to another. Since it's equidistant from one endpoint to another, we kind of made those hash marks ourselves. But we can say that AR is congruent to RM. All right. And since they're congruent by definition of congruent segments, we can say that AR is now equal to RM. Second thing here is we have, or not second thing, fourth thing, it says MB is equal to RM. So point 3 is going to help us figure that out, because if we say um, we have MB is equal to AR, which was the given. So this is kind of like our hypothesis, and this is kind of like our conclusion. And now our conclusion from the first statement is now the hypothesis of the second statement. And now we can say that the first statement, MB, which is right here, is equal to the second conclusion statement, which is RM. That comes from the transitive property. So since we have those two line segments equal, we can also say that those two line segments are congruent. So we could say that MB is congruent to RM by definition of congruent segments. And since those two segments are congruent by definition of a midpoint, we can say that point M is the midpoint of RB, which is the proof. And that is being able to prove statements about segments and angles. Hope this helps. Till next time.